So announcement number one, your Smart Work course is ready. And the code, the sign-up code is on iLearn right now. So if you go to iLearn and you look in the first part of the page there, you're going to see the enrollment key. So you guys can get started with the Smart Work just as soon as you get enrolled. It's a $25 fee to get the homework program. So there's that. That's the good news. Yeah.
Homeworks are due weekly, or?
No, I don't think so. I need to go in and adjust the dates on all the assignments. But what I did the last time I taught this course is I basically just made the due dates on the homework assignments be like the last day of class. So I don't care what order you do the homework in, just get it done before the course is over with and you'll get all the points. Really, the homework is for your practice and that only. And I don't care when you get your practice, as long as you do it as long as you do it. For some reason I can't talk today. I think it's because my brakes went out in my van and I'm really freaking flustered right now. Do you guys know what the sound of brake pads grinding against raw rotor is? Metal on metal? I was listening to that sound for about 30 minutes, 45 minutes yesterday. Just watching my money float out of my pocket. And it didn't pass smog. Anybody want to buy a van? So, I'm not going to throw anything new at you today. We had a lot delivered in those last couple of lectures, and so today we're just going to practice doing problems with what we've learned. Okay? So we've gone over the periodic table, different trends in the periodic table, size trends, electronegativity trends. You're going to be asked questions about all of those trends on the exam. We talked about light and matter. So, what is a photon? How does light interact with matter? Specifically, you're not going to have to worry about that rotation and vibration stuff that I showed you. I just wanted to give that to you to give you an idea of what the mechanics of photon interaction with matter are. But you are going to have to work, you're going to have to do problems like the hydrogen atom, where you look at electron energies as the electrons move from one orbital to another. And you'll have to be able to solve problems that ask you to associate wavelength of transition with energy gap. And we're going to practice those a little bit today. So, something I'm going to point out to you, or actually we're just going to start working through it, is this. This is the practice set of problems that's on iLearn. And so, oh, yeah, there's that, huh? Is that the booby trap chair? I was talking to my housemate yesterday, and I pointed out to him a scar I had on my chin, and he says, "Oh, I've got a scar just like that." And I said, "How'd you get that?" And he said, "I fell out of my chair." That was an awful long fall from it. Maybe it was a really high chair. I don't know. Okay, so this file's on iLearn, and regarding exam 1, the best thing that you can do for yourself for exam 1 is to go through this practice exam. The kinds of problems that you're going to see on this practice exam are highly similar to the kinds of problems that you're going to see on the real exam. More so than even the homework. You should do the homework, but as a priority, you should work through this practice exam. And we're gonna work through it together. Yes. Not for a couple weeks. We got some time. I don't remember the exact dates, but they're all posted on iLearn. If you go to the syllabus already has all of the exam dates. So, I'm not going to lecture. We're just going to go through these and ask the questions. So this is question number 1. It's talking about bonding between atoms, and we end up. Let's see, I should get the answers out on the same screen. Here we go. We didn't list these definitions yet, but essentially, when you've got two metal atoms together, they undergo something that's called metallic bonding. It's referred to as metallic bonding. And this is where, in metallic bonding, you have your atom types that are composing the substance are weakly electronegative. They don't hold on to their electrons at all. And so they describe metallic bonding as an electron sea that surrounds a lattice of positive charge. So in a solid metal, your atoms, your nuclei are fixed in position, and there's a very loosely and weakly bound sea of electrons that surround them. Because none of these atoms has a really high affinity for those electrons that are in the unfilled valence shell, these electrons are highly mobile. If you were to take a battery and put a potential across it, maybe use a capacitor builds a positive charge on one side and a negative charge on the other. You put an electric potential across the metal, and you're going to get electron flow towards whatever the positive side of that potential is, right? That's why you can use metal in conductors, copper wire, yada, yada, yada. It's because those electrons are so weakly bound that they'll bounce around with the slightest push, right? So, metallic bonding is all metal atoms. Now, if you take a metal and a non-metal and you stick them together, what's going to happen, the non-metal being from the right-hand side of the periodic table where you got really small radiuses and really high electronegativities, that non-metal is going to very effectively outcompete the metal for the electron. And so what happens if you bring a metal atom and a non-metal atom together, the electron will get transferred from the metal atom almost completely to the non-metal atom. This will give the non-metal a net negative charge, and it will give the metal a net positive charge. This is what we call ionic bonding. So in ionic bonding, let's say we take a chlorine atom and a sodium atom. If they're neutral initially, by the time they approach, that Cl will have stolen an electron from the sodium. The sodium will have lost an electron, and it will become that positive charge. And so have a positive atom and a negative atom paired together. Salts, as these are called, always form in such a way that the net negative charge is equal to the net positive charge, so that the material overall is net neutral. If the material is not net neutral, if it has a net negative or a net positive charge, we're going to have internal repulsive forces that break the atoms apart and don't allow them to stick together. And so rules for salts is that they're always net neutral, which means that if you got two net negative charges, you got two net positive charges in there somewhere. This is ionic bonding. There's one other kind of bonding we need to be aware of. This is called covalent bonding. And this is the kind of bonding that we get when we take two non-metal atoms and stick them together. The two non-metal atoms are both pretty electronegative, right? They're on the right-hand side of the periodic table again. They've got smaller sized radii. They've got very high electronegativities. And so when you stick two non-metal atoms together in a competition for electrons, what you're going to get is you're going to get possibly some partial charge transfer from whichever one is weakly electronegative to whichever atom is more strongly electronegative. But it won't be the kind of charge transfer that we saw in ionic bonding. In ionic bonding, that electron from the sodium gets taken all the way by the chlorine, and it stays largely localized around the chlorine atom. And it doesn't hang out with the sodium at all. In covalent bonding, you take two nonmetals, they'll stick together and they'll share that electron a little bit better than they did in the metallic bonding. But if one of the atoms is more electronegative than the other, there still will be some charge separation across the molecule. Let's give an example of that. Take a chlorine and a bromine atom. Stick these guys together, and we're going to allow them to make a bond. This dash here indicates there's a shared pair of electrons. If you look at the periodic table, I don't have it up here right now, but if you look at that size trim in the periodic table, you're going to find out that chlorine is above bromine in the column. That means that the bromine atom has a larger radius. They're both halogens. They're both one electron away from a filled valence shell. But because bromine is a larger size, it has a lower electronegativity. What that means, if chlorine has a higher electronegativity, is that of these shared electrons, they're going to be pulled so that they reside more on the chlorine atom than on the bromine. And so the way we indicate that is we draw a little arrow, and we stick a positive end here and a negative end there. That indicates that the charge has localized, the net negative charge is localized towards the chlorine and away from the bromine. This is called a polar covalent bond. It's polar because there's net movement of charge from one atom to the other. It's covalent because while there is charge transfer, the electrons are still shared between the two atoms. It's possible to have a non-polar covalent bond. You take two chlorine atoms, stick them together. They're going to form a bond. They're going to share electrons. But when they do so, the tug of war is even, right? Neither one of these guys wins. It's a tug of war between two animals that are just as strong as each other. And so what results is that the charge density around this molecule it's shared evenly. In that case, we have a non-polar covalent bond. So what you need to be able to do on the exam situation is to take a question, give you two atoms, and say, take this atom and that atom. If they come together, what kind of a bond do they form? Well, you need to figure out, is it two metal atoms? In that case, it's metallic. Is it a metal and a non-metal? Well, in that case, it's ionic. Is it two non-metals? In that case, it's a covalent bond. And you have to be able to determine, in the case that we're talking about a covalent bond, whether or not it's a polar covalent bond or a non-polar covalent bond. All right, so with that, question one. In a bond between carbon and chlorine, what sort of a bond is the carbon-chlorine bond? Carbon-chlorine, two nonmetals, right? They're both on that far right-hand side of the periodic table. And so they're going to share those electrons. So that's going to be what kind of a bond? Covalent bond. Two nonmetals sharing electrons. We've got covalent bond. Now, go ahead.
For the chlorine and the bromine, on the charge density, which one wins on the polar?
Let's show you right here. See where chlorine and bromine are with respect to one another on the periodic table? Bromine is down here. What that means is that they both got 7 electrons in their valence shell. Well, they're both 1 electron away from having a filled valence shell, but the bromine being below the chlorine is going to be larger size, right? It's got 1 extra shell underneath that outside valence shell that's filled. It's got an extra shell that chlorine doesn't have. And if you look at the atomic size charts, you're going to see that chlorine is much smaller than bromine, right? Well, because bromine is larger, it doesn't have as good of a pull on its electrons. Chlorine has a better pull. And so the chlorine atom is going to pull electrons, the shared electrons that it shares with bromine, over towards itself. So chlorine will end up being net negative. It'll have a negative charge density, and the bromine will have a positive charge density. So that would be a polar covalent bond.
polar or non-polar?
Yeah. Well, when it's so polar that we classify it as ionic, then we just call it ionic bond. But, so an ionic bond is a very, very, very polar bond. But in terms of the vocabulary that we're going to use on exams, you're only going to refer to covalent bonds as being polar covalent and non-polar covalent. Right? Does that make sense? All right. So, carbon and chlorine, which one is more electronegative? Yeah?
Can you get a bond between two nonmetals, a covalent bond, so polar that it's going to be as polar as like an ionic bond?
I have no idea what you just asked me.
So an ionic bond is between a metal and a nonmetal, right?
Uh-huh.
Can you get two nonmetals that are that have a bond as polar as a ionic bond?
Yeah, there are certain extremes where that happens, where the difference in the polarity is so great that you do have something that looks almost like an ionic bond. There's gray area in there in how we name things. But in general, if you got two metals, call it a metallic bond. If you got two nonmetals, call it a covalent bond. If you got a metal and a non-metal, call it ionic bonding. Okay. So back to the question, between carbon and chlorine, which one's more electronegative?
Chlorine.
Chlorine. Your halogens over here are always going to be some of the most electronegative species you've got on the table. You can consult a table of electronegativities and they'll give you the exact electronegativities of those atoms. But chlorine is more electronegative than carbon, and so that would be a polar bond with the charge density, a polar covalent bond with the charge density shifted towards the chlorine, because the chlorine is going to win the electron tug of war. All right? So the partial positive charge will be the carbon. The negative charge is going to be the chlorine. Here's one. They want you to look at 3 different elements on the periodic table, whatever Te is, sulfur and rubidium-37. And you're asked to, just from positions on the table, figure out which of these guys is the most electronegative and the least electronegative. You're also asked to relate which one has the largest radius and the smallest radius. So you come up here to the table, and you find these guys, sulfur, rubidium, and Te. So in column 16, you've got sulfur. Column 16, element 16 is sulfur. Go down the column 2 over, and you've got Te. Now, go to the far left of the table, on that same row is Te. And element number 37 in row 5 is Rb, rubidium. Just from those positions, you should be able to figure out which of these is the largest in radius and which of them is the most electronegative, right? The way you do this is you note that sulfur, being higher in a column than Te, is going to have a smaller radius, yeah? Because Te's got way more filled subshells underneath of it than does sulfur. And so sulfur is going to be smaller than Te. Sulfur will therefore be more electronegative than Te. Now you compare, so you've already ranked sulfur and Te. Sulfur is the smallest and the most electronegative. Te comes in second. Now you know Te's position on the table with respect to Rb. Rb is way over there on the metallic side of that row that they share together, which means it is the largest sized atom and therefore the least electronegative. So you've ranked Te and Rb. Rb is larger and less electronegative than Te. So you've got a ranking between Te and sulfur by looking at the column. You've got a ranking between Rb and Te by looking at the row. You put those together and you can rank these. Sulfur is the smallest and the most electronegative. Te comes in second place in terms of size and electronegativity. And Rb is the largest and the least electronegative of that group.
It's the opposite, the larger the atomic radii, the more electronegative.
The larger the atomic radii, the lower the electronegativity. So in these kinds of problems, you're gonna see the following vocabulary. We'll be asked about the radius, size. We'll be asked about the electronegativity. And you'll be asked about the ionization energy. Now, electronegativity and ionization energy are inversely proportional. The more they're directly proportional. So electronegativity and ionization energy are directly proportional. The more electronegative you are, the harder it is to remove an electron. Ionization energy, the vocabulary, means the energy that you have to put into the molecule or at the atom, in order to separate its electron. So remember, when you got an electron bound really tightly to a nucleus, you're in a low energy position. But if you want to separate them, you're going to have to put energy in to fight against the attractive forces. Well, ionization energy means the total amount of energy that you have to put in to completely remove this electron and drag it out to infinity, an infinite distance away from it. So you should be able to know the larger the radius, but the smaller the electronegativity, therefore the smaller the ionization energy. Yeah? Now, the last couple questions were just asking you about ionization energies and sizes, the same way that first one did. But down here at D, you guys see D, it says identify the number of core electrons and the number of valence electrons for each of these elements. And they start listing elements. Well, core electrons mean everything that is in enclosed shells, right? Let's go back up to our periodic table for a second. So anything that's any electron that's tucked away in a closed shell is a quote-unquote core electron. One of the reasons they call them core electrons is because the electrons that are in closed shells are not removed very easily at all. In fact, they play very little role in bonding because they're held so tightly to the nucleus. Your valence shell electrons, the ones that are not in closed shells, those tend to be the electrons that are held more weakly by the atom and are exchanged or transferred in bonding with other atoms. And so we learn to differentiate between the core electrons and the valence shell electrons, largely because it's the valence shell electrons that we know governs bonding for the atoms. So go up to the table and look at an atom. Let's look at chlorine. Actually, let's look at aluminum, number 13. Can you guys tell me how many core electrons and how many valence shell electrons aluminum has? Aluminum is the third element in row 3. So that means that its valence electrons are in that third subshell. It's the third subshell in aluminum that is being filled and is not yet filled. All right? The two shells below it, or above it, are the closed shells. That first shell that has 2 electrons is filled, and that second shell, corresponding to row 2, that has 8 electrons is filled. So it's got 10 electrons tucked away into its closed shells, and then it's got, in the neutral atom, 1, 2, 3 electrons in its valence shell. Yeah? So if I asked you how many core electrons, how many valence electrons, for aluminum you would say 10 core electrons and 3 valence electrons. So be able to do that. Alrighty. A lot of these questions are very similar, so I'm scanning through the ones that we've already kind of addressed. Now here's one that a subject I haven't exactly addressed, but you should be able to put it together from knowledge of the periodic table. It says, predict the kind of ion, this is F here, predict the kind of ion that rubidium and sulfur will form. Now, to be able to predict ion types, you're you're gonna have to realize something. And that is that for the nonmetals, back here, keep going back to this table. For the nonmetals, say we're looking at calcium. Calcium's got 2 valence electrons, right? And it's a big atom, very weak electronegativity. Those electrons are not held on to very tightly. You'll be able to easily, in bonding with other atom types, electronegative atom types, you'll be very easily able to remove those 2 electrons. But once you get those 2 electrons away, if you're going to try to pull another electron off, that next electron is going to have to come from that closed shell. So calcium, the unfilled shell, is the 4th shell, but it's got a filled 3rd shell. Well, the electrons in that 4th shell aren't held very tightly, right? They're at a further radius away from the nuclear charge, and they also have more electron density to look through. But if you pull those guys off and then you go in deeper and you try to pull off one of those electrons from a closed shell, well, now that electron is actually closer to the nucleus, and it has fewer electrons to look through to see the nuclear charge, and so that electron is held very tightly. Take-home message then is that for calcium, you're only going to be able to ever pull off about 2 electrons. So the ion type that calcium is going to make will be the Ca2 plus ion after it loses 2 net negative charges. Good luck trying to make the Ca3 plus ion. To do that, you're going to have to pull out one of those electrons from a closed shell, and that is not going to happen very readily. I mean, it'll happen in like a nuclear reaction or something like that, where the atoms are all splitting apart and flying to pieces. But in regular chemical reactions, you're not going to see Ca3 plus. You're only going to see Ca2 plus. Okay? Does that make sense? All right. Now let's take that same piece of logic and let's ask ourselves about what kinds of ions these nonmetals will have. So the metals have the characteristic that they tend to make positive ions because they've got these weakly held electrons, right? Big, large radius, weakly held electrons. Those electrons get stripped away. The nonmetal atoms are the opposite of that. They're so small, and any electron that would come and join them has so much force that it feels from the nucleus that they'll take on extra electrons, more electrons than they would have in the neutral atom. They'll become negatively charged ions. Now let's do a thought experiment here. Let's say we're oxygen, right? Do a little drawing here. Oxygen has 2 openings in its unfilled shell. Right? We're in column or row 2. We've got an ability to put a net of 8 electrons into that second shell. So let's just draw it real quick here. A bunch of positive charge in the nucleus. In our first shell, we've got 2 electrons. We've got room for 8 in the outside shell, but we only have 1, 2, 3, 4, 5, 6. That means there are 2 open spots in that outside shell where electrons can surround that oxygen atom. Well, again, because these spots here have the same radial separation distance as the spots of these other electrons, they feel just about the same pull from the nuclear charge that these guys do. And so what will happen with oxygen is it'll tend to accept an electron into this position, and it'll accept an electron into this position. Right? It takes on 2 electrons. But after that's happened, that shell is closed. You can't fit any more electrons into that shell. So if you were to try to throw another electron onto that oxygen, that electron would have to kind of go out here at a further separation distance where it doesn't see as much of the nuclear charge. It doesn't feel the same forces. That's not going to happen. That electron's not going to land there. Oxygen's only going to pull 2 extra electrons. What's true about your nonmetal atoms is that they will tend to accept, as if they're paired with the right partners, they'll they'll tend to accept as many electrons as they need in order to fill whatever valence shell it is that is as yet unfilled. But after they've taken on enough electrons to fill that shell, they'll stop taking on electrons. All right?